Mechanical vapor recompression, or MVR, is the most energy-efficient evaporation technology currently available.
Consortium Enviro Solutions.
As industries face increasing pressure to reduce energy consumption, electrify thermal processes and cut CO2 emissions, MVR evaporators have become a key solution for wastewater treatment, product concentration, and resource recovery. At its core, an MVR evaporator operates as a closed-loop energy recovery system. In conventional evaporation, the vapor generated during boiling is condensed and its latent heat is rejected through cooling systems. This represents a major energy loss. In contrast, an MVR system captures that vapor and it reuses it. The vapor generated in the evaporator is routed to a compressor, where its pressure and temperature are increased. Once recompressed, the vapor returns to the heat exchanger and it condenses. This releases latent heat that drives further evaporation. The process becomes a continuous internal energy reuse cycle in which the system largely feeds itself. Electrical energy powers the compressor, raising the enthalpy of the vapor and enabling its latent heat to be reused as the primary heating source. As a result, external thermal energy demand is drastically reduced, and in many installations, steam consumption can be nearly eliminated. In terms of performance, MVR evaporators stand out for their energy efficiency. Specific electricity consumption typically ranges between approximately 10 and 55 kilowatt hours per ton of evaporated water, depending on the temperature lift, compressor efficiency, system configuration, and the feed characteristics. Compared to conventional thermal evaporation, this can translate into energy savings in the range of 50 to 80%, particularly when we talk about replacing single effect or low efficiency multiple effect systems. Temperature lift plays a decisive role in this performance. It represents the difference between the evaporation temperature and the condensation temperature after compression. Lower lifts result in a lower compressor power requirements and higher overall efficiency. As the lift increases, compressor energy demand grows rapidly and system performance begins to decline. The compressor is therefore a central component of the MVR system and largely determines operational stability and cost. Another key indicator is the coefficient of performance, because most of the heat required for evaporation comes from recycled vapor rather than from external energy sources. MVR systems can achieve very high effective thermal efficiencies compared to steam-driven evaporation. From a mechanical and a process engineering perspective, MVR evaporators can be configured in different ways, and this depends on the properties of the feed stream. Falling film designs are often selected for fluids with low to moderate fouling potential, offering high heat transfer efficiency and short residence times. Forced circulation evaporators are better suited for streams with high solids content, scaling tendencies, or high viscosity, as they reduce fouling risks and provide most robust operations. When compared with traditional evaporation technologies, the advantages of MVR are significant. Energy consumption is drastically reduced because latent heat is reused internally. The need for external steam is also minimized, and evaporation can be fully electrified. Operating costs decrease as fuel demand and cooling requirements drop, and environmental impact is reduced through lower CO2 emissions. Additionally, MVR systems integrate well into circular process strategies by enabling water reuse and the recovery of valuable compounds. From an engineering perspective, MVR is not always the optimum solution, and understanding its limitations is essential for correct technology selection. In applications with high boiling point elevation, such as, for example, highly concentrated brines or viscous chemical streams, MVR performance can deteriorate significantly. Capital expenditure is another consideration. MVR systems require high-performance compressors, advanced control systems, and robust heat exchangers, leading to higher initial investment costs compared to some of the thermal alternatives. Operational stability is also sensitive to fouling and scaling. Unstable vapor generation, variable feed composition, and intermittent production can affect compressor operation and process continuity. In these scenarios, other evaporation technologies can outperform MVR from a technical and economic standpoint. Electrical heat pump evaporators, for example, often provide better performance at lower evaporation temperatures and moderate concentration requirements. They are particularly effective when temperature lifts are small and when precise thermal control is required. In such conditions, heat pump systems can achieve comparable efficiency with simpler mechanical configurations and lower compressor loads. Thermal multiple effect evaporators, on the other hand, remain highly competitive in environments where steam is readily available at low cost, where very large evaporation capacities are required. By cascading vapor energy across several effects, these systems achieve strong thermal efficiency without relying on high electrical power input. They can also outperform MVR in applications requiring large temperature differences, heavy-duty continuous operation, or high tolerance to feed variability. In practice, the choice between MVR, electric heat pump, and multiple effect evaporation depends on a balance of factors: electricity price versus steam availability, required evaporation capacity, temperature lift, feed composition, fouling behavior, and plant operating profile. At Condicam Enviro Solutions, we have delivered hundreds of evaporation projects. We design and install a wide range of vacuum evaporators, selecting the technology that best meets each customer's specific needs.
Condicam Enviro Solutions.